Thank you. So first I would like to thanks all the organizers for the invitation, and I'm very sad not to be able to be in person, but as we all know, all Europeans are forced to be remote. I was waiting to the last moment for that. I would come if I could, but I couldn't, unfortunately. So before I start, I wanted to acknowledge my group in UCL, and especially Alex, Connor, and Cristobal, whose work I will be presenting, and also the funding from EPSRC and our Quantera network. So I will start by giving like a general introduction to the problem, saying that in the last decades, I would say a new field emerged of quantum fluids of light, where photons were placed in specially engineered structures, which make them interacting, in some cases even strongly interacting. But as with photons, you have to picture that there will always be dissipation, and one needs the drive to sustain a steady state. So over the last decade, both theoretically in various groups as well as experimentally, we studied this problem in terms of looking at non-equilibrium phase transitions, various critical phenomena, non-equilibrium superfluidity, topological defects, and phase transitions. So this whole field is quite relevant to the subject of the conference. Especially, there's a lot of overlap between driven-dissipative photonic systems and classical systems. But since I've given quite a number of talks in KTP about this physics, I decided to give a talk today about something related, but not exactly that. So I will talk about now placing the photonic particles, interacting photonic particles into lattices. And these lattices can be engineered in various ways. And there are various systems which can host interacting photons in lattices. But in particular, two systems which we will be working on in our group, and which I think are the most advanced experimentally, are polariton lattices, like for example, polariton micropyral lattices and circuit QED lattices. So in terms of polariton lattices, quite a lot was done on the single particle level, quite a lot of interesting physics, including all the topological phenomena such as flat bands, photonic graphene was realized, a lot of topologically protected states has been seen, but not yet, the interactions were present, but not yet very strong interactions. At the same time, we know that, and we heard also talks in KTP about circuit QED lattices, and dissipative phase transition has been observed there. And especially the system is interesting, and it can give rise to hyperbolic lattices and curved spaces. So you can ask a question: how can we treat strongly interacting photons in the driven-dissipative environment? So when the dissipation and drive and dissipation have to be treated on an equal footing as interactions, but and if we want to go to systems which are larger, so we want to go to thermodynamic limit to look at many body phenomena, we know that exact diagonalizations or any exact methods will not work. So we need effective methods to strong correlations and entanglements, but in the driven-dissipative lattice systems. And that's very relevant questions for current experimental platforms looking at light matter interactions. So in our group and in general, I would say, you can approach this problem from two different directions. So one direction which we have been using and we have been working on quite a lot is phase space methods, which are extremely good for studying non-equilibrium weakly correlated systems, such as which I mentioned at the beginning. But how to use them, how to extend them to stronger correlation to look at entanglement is not so easy. And on the other hand, we know that tensor network methods are very, very good for strongly correlated systems, but at the same time, till now, there was not really any working algorithm for driven dissipative system in two dimensions. So I don't know how much time I will have to cover all the topics what I plan to cover, but we in our group we're approaching the problem from these two directions, and I will first start from phase space methods. So in particular, I would like to advocate that phase-space methods can be very good for systems with drive and dissipation, and especially we develop kind of approach based on positive P method for driven dissipative lattice of bosons, which have been recently published in PRX Quantum. So in general, positive P is a stochastic method, so it's a very kind of efficient computationally, just solving stochastic equations for many times. And of course, it's an old method. It has been suggested for closed system a long time ago. But the problem is that it was not very useful for closed system. There was very little applicability of the methods. There was only very limited number of problems where the method was converged. So although the method is exact, it's computationally very unstable, and the trajectories very often go to infinity. However, in our work, we showed that in open systems, this situation improves substantially. So it turns out that drive and dissipation somehow dumps the entanglement to the extent where the trajectories actually get stabilized, and the applicability of positive P is much larger. So we looked at, in particular, we looked at Bose-Hubbard, driven dissipative Bose-Hubbard model in that context. So what is positive P method? Well, so for any driven dissipative system, one would start from Lindblad master equation, for example, with some dissipation terms, and that can be mapped to Fokker-Planck equation. And finally, Fokker-Planck equation can be mapped to stochastic differential equation. A sister method to positive P, which is well-known truncated Wigner method, would rely on making some approximation in the Fokker-Planck equation, so that one only has a single stochastic equation for one field variable. And truncated Wigner is always solvable, so there is never any numerical problem with it, but it just, because it's an approximate method, it may not describe your problem very well if the quantum correlations are strong. Positive P does not require any approximation whatsoever, but one doubles degrees of freedom, so one has two couple equations for the stochastic variable. And if the method works for your problem, it's an exact solution, gives you an exact solution. It's also very easy to compute any observables, any moments to any power by just taking an appropriate averages over stochastic trajectories. So we have implemented that for driven dissipative Bose-Hubbard model, which contains a drive, coherent drive, and incoherent dissipation in the system. So the exact dynamics of such a model will be described by these stochastic differential equations, which can be very easily solved on the computer. And moreover, obviously, Bose-Hubbard model has been, driven dissipative Bose-Hubbard model has been studied before by kind of different methods, such as corner station normalization, for example, but those methods were only able to treat a few lattice sizes, as they are not very well scalable as the system sizes is increasing. Positive P scales linearly with the system size. So unlike other methods which were able to treat two, maybe 4 by 4 maximum lattice sizes, we are able to treat hundreds by hundreds of lattice sizes. So in the regime where it works, it's really very computationally efficient. So with Paul, with Piotr Dwer and my PhD student, we explored the whole range of the driven dissipative Bose-Hubbard phase diagram, looking at various levels of dissipation. So this is a drive parameter in the units of interactions, and this is decay parameter in the units of interactions. So all the colors, so green, blue, and yellow, are cases where positive P was working and giving the exact solution to the problem. So you could see that it worked very well in the regime where there is strong dissipation. It didn't work well in the regime where there's strong drive, but luckily this regime is very easy because the strongly driven regime is semi-classical. So you'd have a feeling that methods which are a little bit approximate would describe that regime, and that's what we checked. So we run truncated Wigner calculations on the regime of strong drive, and then obviously positive P everywhere. And we found that between truncated Wigner, which is basically an approximate method, but it gives accurate results in semi-classical regime, and positive P method, which is an exact method, but it just sometimes doesn't work, we were able to cover almost entire phase diagram of the driven dissipative Bose-Hubbard model, apart from this corner of very small dissipation. So basically, if your dissipation or your drive, or both of them, are smaller, much smaller than interactions, then the phase space methods will not work. However, if you are in a kind of more strongly damped or strongly driven regime, then the phase methods are really very good. And I would like to advocate the use of these methods in that regime. But then one could ask a question, okay, maybe it just happens that we are killing with a driven dissipation all quantumness, and then there's no wonder that the phase-based methods are actually working. But we checked, and this is not the case. So this is an example of if you take just one pillar, so out of the Bose-Hubbard model, you just take one lattice side, and there is an exact solution to the driven-dissipative problem, which is given by the black line. So this is occupations, and this is the correlation function G2. Running positive P, we could see that we could reproduce exactly. The results were lying on the exact solution. However, truncated Wigner would completely fail to describe correlation. Truncated Wigner was actually good to describe the occupations, because occupations can be described easily even by mean field calculations. This is not difficult to describe. But if you really wanted to look at correlations such as G2, the truncated Wigner was not good to describe that. However, we could see that there was either we were in the anti-bunching or bunching regime. So it's not that the system was tuned to the regime when it was classical. It was actually quantum. There were quantum correlations present, and positive P was able to describe that. If you now extend to larger and larger lattices, so similar things can be observed. So if one looks just at the condensed fraction or phase, then obviously going to larger lattice sites, it just improves a little bit. So the system is converged even for the lattice sites which are small. So green is 2 by 2 lattice sites, and blue is 100 by 100 lattice sites. And the black line is self-consistent mean field calculations, whereas these noisy lines are the positive P calculations. And we can see, obviously, that, again, the kind of more classical variables such as condensed fractions or phase or occupations are easily described by any methods. But if you wanted to look at correlations in the system, so G2, so if you ever wanted to look at kind of interesting quantum phenomena, then obviously we're very far with the exact dynamics from the self-consistent mean field. But moreover, also we discovered that one often needs to at least 100 by 100 lattice sites to describe the system correctly. So looking at the state of the art so far with corner renormalization or some other exact methods, as I said already, that only few lattice sites could be considered. And so we advocate that quantum correlations are not well described by approximate methods. One has to go to the exact methods. But large systems are needed for convergence if one wants to look at the nature of the correlations, nature of the states. But positive P scales linear with the system size, so we advocate it as an excellent method to look at those problems. Moreover, and that's what we also shown in the calculation, is that this method, unlike some of the tensor network methods or some other exact methods, does not rely on any ansatz for the ground state. So you can put any spatial dependence. So that Piotr used a log of the Institute of Physics in Warsaw. So this is a Bose-Hubbard model on that completely weird lattice with no symmetry whatsoever. But space and time dependence of parameters is just completely not relevant for the algorithm. One can easily solve that as easily as any lattice with translation and invariant symmetry or with any symmetry. And similarly to other things, to earlier results, we could see that unlike occupations, so the black and green are, black is self-consistent mean field, green is Gross-Pitajewski equation, and the blue is our result. So looking at occupations, obviously you don't need to look at an exact solution to quite well describe the occupation. But if you look at G2, so again correlations, the red is an exact solution, whereas the black and green describes what would one get from Gross-Pitajewski or self-consistent mean field. So the exact solution is actually quite different. So motivated by this, we are now looking at realizing a fractional quantum Hall effect with polariton lattices. And so this is a work which we submitted with Cristobal recently, taking a polariton micropillars, but arranging them with distances between micropillars which grow linearly or decay linearly in space. This can be translated. Yes, so this can be translated to an effective magnetic field, and this gives rise to Landau levels in the system. So we were able to simulate that system and observe that the condensation is taking place into the Landau level. So we drive the system completely uniformly, but the condensation is taking place in the Landau level, which has a vortex lattice, because the Landau level will have the rotation in the wave function. So now obviously, for just getting the normal, the integer quantum Hall and condensation into the quantum Hall states, positive P is not necessary. Truncated Wigner would be enough to describe that. But if you want to go now to fractional, so if you want to increase interactions or decrease the occupation to go to fractional quantum Hall, then we need to account for quantum correlations, and that's what we are doing now with positive P. I just go perhaps a bit quicker. So okay, so I advocated that if you are really strongly damped or strongly dissipative, the phase space methods are excellent, and then we can look at many problems now using, for example, positive P. But what about this corner of the phase diagram, which is, of course, is interesting. I mean, there is dissipation and drive, but not so strong, so the interactions are dominated. So obviously, phase space methods will not work there, and what we in our group, what we explore to address that corner of the phase diagram in general is the tensor network methods. So, I mean, everyone knows tensor network methods, probably I don't have to review that, but I have to say just that the tensor network methods are very well developed for one-dimensional systems, or a little bit more for one-dimensional driven-dissipative systems. But for two-dimensional driven-dissipative system, there is nothing. So the early attempts of algorithm published in 2017 were later shown by Jonathan Keeling group and by our group that this algorithm was not converging in their bond dimension. So you couldn't really get any physical results using that method. So the question was, okay, what can we use? So can we actually design a method which would which would calculate dynamics in steady state of driven dissipative, but two-dimensional open quantum lattice models. So that's what my PhD student Connor was able to achieve, and the details are published in this PRX 2021. So I won't go too much through the algorithm, otherwise, I mean, we have very little time, but it was just taking ideas from equilibrium systems and putting them together, and luckily making the whole algorithm work for driven and dissipative systems. So representing the state as IPEPO, integrating equations of motion using time evolving black decimation, but unlike this nature communication work, we treated the full environment, I mean, we provided a full environment truncation and fixing the network to weighted trace gauge. So these ideas were already around in the context of closed system, but they were never implemented for open driven dissipative system, and luckily in our algorithm we were able to show that they work. So we tested that with transverse field dissipative Ising model, for the reason is that if the H is set to 0, this model is exactly solvable. So we were able to compare our simulations with an exact solution. And we went through strong damping, moderate damping, and weak damping to see how the algorithms compare. So I don't have maybe time to go through details. This is just magnetization and various correlations, so spin-spin correlations in the system. And we found that, so the blue is the bond dimension 1, so it is equivalent to mean field. The dashed line is an exact solution. So you can see that correlations are very non-mean field. So the mean field does not describe the system well. But as we increase the bond dimension, we are able to converge into the exact solution. So that we checked that for strong damping, for moderate damping, and weak damping. And as expected, of course, weak damping is always the hardest to examine, as the drive and dissipation provides the kind of killing of some of the developing correlations. But even with the very weak damping, we're still able to get quantitatively the right results. And then we applied to this model with H not 0, which of course does not have an exact solution, and there is no any other method which was able to treat that. So in some sense, quantum simulator are needed to check whether our results are correct, but they were confirmed. So with that, we wanted to address a real problem. So now we had an algorithm for two-dimensional even-dissipative systems, and we looked at specifically an anisotropic dissipative XY model. It's an interesting model because in some sense there is a competition between dissipation, who is causing the decaying towards the sigma z down state to the pure state, but at the same time, because of anisotropy, there is an effective magnetic field perpendicular to the spin. So this model has quite a rich magnetic possibility for rich magnetic phases, but moreover, it is PT symmetric. So one can expect a transition, some kind of phase transition between states which are pure and maximally mixed. And it was predicted by mean field theory that this model gives rise to spontaneously symmetry breaking staggered steady state phase. So the spins will form two sublattices, A and B, and will arrange themselves with some angle to the sublattice, but in opposite directions. So you have a staggered, this kind of staggered phase. And obviously, this phase of the spin to the Z direction phi, it's a free phase. So, I mean, there's spontaneous symmetry breaking, so one obtains vortices and anything to do with the topological phase transition. However, although mean field showed this very interesting staggered phase, so symmetry breaking is a staggered phase, the Keldysh field theory, looking at fluctuation, looking at long wavelength limit fluctuation, actually show that this phase is never stable, because the model could be mapped to classical XY, but being always above BKT transition. So because of the way of the dissipation acted on the interaction, it always was above BKT. You could never tune the system to be below BKT. So we looked at that with an exact method to see. I mean, Keldysh, it's great, but obviously it's just long wavelength limit. It's not that all fluctuations are included in that, and there were quite a number of approximations being made, which basically just boiled down to saying that the system is always above BKT. So we perform an exact computation with tensor network methods, and as we increase the bond dimension, you could see that the transition was indeed gone. So this is a magnetization as you increase the bond dimension, and finally, as you increase more and more correlations in the system, there is no transition. And that's also showed the magnetization in time. So even if you start with this staggered phase initially, as you increase time, the magnetization will be gone. So the staggered phase does not survive as you increase the bond dimension. D is the bond dimension. However, now the tensor networks allow us to look into the nature of correlations, as well as just saying, okay, the transition is gone. So we look at the correlations between spin at G1 at the distance, and we could see that there is no algebraic order. So the correlations were decaying exponentially with exponent actually close to 1. But there was, so if you look at a correlation between red, only red, so kind of looking at every even or every odd, so blue and red, it's a different type of correlations, because these are correlation between different, either the same sublattice or different sublattice. So the one was just 0 always, whereas the other one was showing a decay at the rate, I mean, e to minus r over xi. So there was a reminiscence of these correlations, which were which the mean field was kind of predicting. And then the last moment, this is the last slide, we also looked at entanglement as you go across the transition, because we're kind of trying to see if because it's a PT symmetric system. So as you move from a pure state to a maximally mixed state, so going across the phase, changing the dissipation. So this is a very strong dissipation. This is a very weak dissipation. Obviously, magnetization changes, but we could see only the smooth crossover between these phases. However, so this is an entanglement negativity and entanglement entropy. However, an interesting point was that if you look at the phase diagram, so the mean field phase transition was present here at 0.25. And we could see that there is a peak in negativity, entanglement negativity close to that phase transition. So in some sense, although the order is gone completely, there is a very large peak in quantum correlations around where the transition would otherwise take place. So basically, with tensor network methods, you could have a much stronger insight into the correlations in the system, even if you discover then there is no phase transition in there. So now we are looking at a number of models which actually we expect that there would be a phase transition, and wanted to see whether the method can also describe phenomena when there is. So just to conclude, I wanted to say that dissipation present in photonic platforms helps in performance of both stochastic and tensor network methods. We were able to make them both work thanks to the dissipation, so thanks to the fact that some of the entanglement was lost and the trajectories were not escaping to infinity, as in the case of positive P, or also in the case of entanglement. If you do dynamics, you know that sometimes in the short times your whole dynamics can blow up because of the growth in the entanglement, but the dissipation is helping to overcome that. However, at the same time, it's not that we are throwing the baby with the bath, that okay, we're describing classical systems. Quantum correlations and entanglements is still present, although to the lower extent in these driven dissipative systems, but to the extent where it's possible to describe with this method. And in some sense, we're hitting, I mean, we're using, doing the calculations with this method, but at the end of the day, there's nothing really to compare it with. So because this is a state of the art in terms of the computing. So in some sense, we need physical quantum simulators to verify and cross the limits, such as, for example, circuit QED lattices or these polariton micropillars, for example. So I'm really sorry for overrunning, and thank you. That's my final slide.
Thank you, Marzena. There are applauses, and anyway, no worries, because you went over time. We'll then take probably only one or maximum 2 short questions, because I want to stay in time. That's also a remark for all the other speakers. I mean, if you want to overrun time, we are here to learn physics, right? But we are going to kill discussion because I want to respect the timing of KITP. So are there questions from in-person or online people? So raise your hand or just go directly to the microphone.
Maybe I have a quick technical one. So can you, with these methods, also assess 2 time correlation functions or temporal correlation functions, or is this incredibly more difficult?
No, it's not. So, no. Yeah, you can calculate. Yes, I mean, with stochastic methods, it's just it's very easy. Yes, so you can just shift. You obtain your quantum trajectory, and you can just shift that in time. So, yeah.
And with the tensor networks?
Tensor networks, we didn't look at 2 times correlation functions, but I would expect, because there are different things are easy in the tensor networks than in the. It's much easier to look at entanglement, entropy, and in the language of tensor networks, and it's much easier to look at correlations in the language of stochastic methods, because in the stochastic you can just calculate any level of correlations in time or in space. But I would also think that it should be possible because you get the whole density matrix in tensor networks, so you could just calculate the time correlations as well. We haven't done that.
Thank you.
Other questions?
Just a quick question. So for the positive P method, can you actually apply it to quantum spin models? To spin models, to quantum spin models.
Yes, so this is something which I skipped due to lack of time, but we are, so I'll just put a cartoon in some sense, but at the moment we are developing that method for spin models. And you can do it in 2 ways, either represent your spin in terms of coherent state and it has some problems. Or you can represent, you can take the spin and map it to bosons. So if you represent the spin as bosons, this is very easy, and we already have preliminary results showing that it actually works. So the difficulty with representing it as bosons is that sometimes if you want to start with some specific initial state for the spin, which is not easy to describe with boson, you might have problems. But if you are interested in the kind of more driven dissipative systems, which are not sensitive to the initial conditions, but they will arrive at some steady state which is independent, then you don't have this problem. Whereas the coherent state for the spin has a problem that it's very difficult at the same time to describe spin up and spin down. Because if you describe spin down by something, then spin up would be like infinite. You need like an infinite. But then one can regularize that, and it's also possible to go over. Like at the moment, we could see that the most promising direction is basically represent spins as bosons via transformations, and then you can apply that to the like in a very similar way to the bosonic case. And we are now looking at a couple of like physical examples to see how it works in practice. So far it looks promising, but I didn't put the results because it's still preliminary, and there is also like it was only 20 minutes talk. So
thank you.
So I think that was a very nice set of technical progress, I have to say. And I'm gonna read also the papers with more care. That was very nice. Unfortunately, Emily, I'm sorry, but we have to move to the next talk. That's because we got compressed by the main speech. So if Zala can share slides, we thanks again, Marzena. That was quite instructive to learn how you're doing these things. And you can directly share screen, Zala.